In this section, let us go deep dive into running Spark workloads on Kubernetes or Amazon EKS in general. Let's get started. So how does the Spark work on Kubernetes? Let us say we have an EKS cluster and we have created one namespace called Spark operator. This is where the Spark operator engine will be running. Then we have one more namespace for the users to submit their application. So this is called Spark Team A. You can have multiple namespaces corresponding to each of the data team or the data scientist team. So the data engineers will submit the Spark jobs via the Spark Submit API. And this API is going to talk to the API server, which is front-ending the Kubernetes control plane, and the Spark operator, which is running inside the Spark operator namespace, will be watching over this custom CRD called Spark application. So it will watch over this CRD and then take the appropriate action to run the job. So it then creates a Spark driver pod in the Spark team A namespace, and the driver contains multiple functionality. One is the core Spark core runtime engine, and there is one more component called Kubernetes scheduler backend to schedule the additional executor nodes pods. And the Spark driver pod exposes multiple ports for different functionality. So one of them is a driver port and another one is a block manager port. And the Spark driver, after executing in the cluster, will request the API server to run the executor pods. And there could be many executor pods running in the same namespace to run the Spark application. And each of the executor pods can have corresponding CPU and the memory configuration as defined in the Spark application. The executor pods will connect back to the driver pod using the cluster IP of Kubernetes, which is for the Spark driver service which is created. So using this cluster IP, which has a static DNS name and the corresponding port, for example, the driver port, the Spark executor will connect back and communicate. And the Spark context object within the Spark driver will send the required instructions to the executor to run various tasks on that executor on that node. So let us understand some of the concepts when running the Spark workloads on Amazon EKS. So one of them is the mode in which the Spark is running. So there are two modes. One of the mode is the cluster mode. So in this mode, we need to mention the -master as one of the option to the Spark Submit API, and the Kubernetes control plane API server URL needs to be provided as an argument to the master variable, master argument. And the deploy mode is cluster. So this is recommended for the production workloads. There is one more mode called client mode. So in the client mode, important consideration is for the networking because the executor pods needs to connect back to the driver pod using a static stable host name. So that means the headless service in Kubernetes can be leveraged and a static name can be provided to this pod, driver pod. Then another thing we need to keep in mind is the owner reference for garbage collection. So what exactly does it mean? So when a driver pod is complete and if you provide the reference of the executor pods to reference the driver pod using the owner references, and when the driver pod is completed and terminated, the executor pods also will be terminated along with the driver pod. So that way it's easier to do the garbage collection. From a security point of view, the authentication is not enabled by default between the driver and the executor pods. And the default user which Spark uses is UID of 185. We can override this using the user directive in the Docker file, and using that we can provide least privileged Linux capabilities to the driver and the executor pods on the host. You can also use a powerful feature which is pod template. Using that you can provide a customized security context field, and using which you can further provide the permissions very granular level to the pods. It could be driver or the executor pods. Then host path volumes you can leverage if required, otherwise you can avoid them because it's also a sensitive security issue to access the host path to the pods. Then both IPv4 and IPv6 are supported in Spark, and from version 3.4.0 onwards, only IPv6 environment is also possible. So for example, by default, the configuration will support IPv4 using two variables, IP family policy and IP families. But if you wanted to do only IPv6 based clusters, then you can use this variable IP families and set it to IPv6. And Spark also provides lot of dependency management. For example, if you have the input files or other dependents libraries and files available at various locations, you can use either local um, colon slash slash or Spark extra class path environment variables as well. And if you have some data in S3 or local file system from where you're running the job, you can also reference these paths directly using the Spark configuration. Then from a secret management point of view, Spark allows to use the Kubernetes secrets to store the credentials. It could be username and password, security tokens, things like that. You can use the Kubernetes secrets, or you can also use the environment variables for the applications and reference the values for this environment variables from the secrets. So both options are possible for secret management. Now, pod template, as I mentioned, is a very powerful. So by default, Spark provides lot of configuration options when running the job. But if some of the configuration is not possible through the default Spark configuration, then we can use the pod templates to provide some additional extra customized configuration. So we can have a dedicated template for the driver as well as the executor pods, and these can be hosted in S3. And Spark allows multiple options for configuring the volumes for the Kubernetes pods. So you can use the host path, empty directory, NFS, or the PV. Another important consideration is basically the PVC oriented executor pod allocation. So what exactly does it mean? By default, when the executor pod is deleted, the corresponding PVC is also deleted. That means when a new executor pod is created, then the new PVC has to be created. So to avoid this, you can enable this configuration here, which is on persistent volume claim is equal to true and reuse persistent volume claim is equal to true. So this means the ownership of the PVC lies with the driver pod. So whenever the executor pod gets deleted, the PVC is retained and will be reused for the new executor pods by the driver pod. So that way you can save the time from creating the new PVCs.